Hi, I am presenting our work Anticipatory Planning for Performant Long-Lived Robot in Large-Scale Home-like Environments. Consider the setting where a robot must complete a sequence of tasks in a persistent large-scale environment given one at a time. For example, the robot is asked to serve water at desk. Later it may be asked to clean the jar or wipe down the table, tasks drawn from a task distribution. Lacking knowledge about the future task, existing task planner focus only on the immediate planning cost and do not consider how their actions might affect the future task, hence performs poorly for long-lived task sequence. So we use an approach that considers both. Anticipatory planning, formalized by Dakale et al. This approach minimizes both the immediate cost and the future expected cost, also known as the anticipatory cost, to improve long-lived planning performance. It is computationally challenging to compute the anticipatory cost online, so we need to estimate it instead. Their approach performs well in small block world setting, but anticipatory planning requires search over possible plans and estimate their expected cost, which becomes challenging as the environment grows. In these large settings, there are many assets and multiple rooms that makes both the learning and planning intractable. We scale anticipatory planning to home-scale environments requiring contributions in both scalable planning and learning. To address the challenges of learning at scale, we abstract the world as a sparse 3D scene graph-based representations to define a graph neural network, which we use as our anticipatory planning cost estimator. In our graph representations, nodes are the entities embedded with semantic features, and edges represent the relationships among the nodes. Our insight is that this representation is well suited for the GNN to learn at scale. To accomplish anticipatory planning, we must search over possible plans and select the ones with lower overall expected cost. But as the environment grows, there could be many plans that satisfy a task, making this search intractable. For example, given the task serve water at desk in these environments, the robot could select a clean cup to fill it up with water to serve, or it can select a dirty cup and clean it before serving water in it. Similarly, it can also clean a dirty jar and fill it and serve water from it. To mitigate the exhaustive plan generation, we use a focus sampling based procedure by augmenting the original task with limited set of predicates and reduce this sample space and select the plan with lower overall expected cost, estimated using our GNN. We show the effectiveness of our approach in large restaurant and proctor environments. For example, in one of the restaurants, the robot is given a sequence of two tasks, one to serve water at table 1 and 2, then to serve water at table 2. Mapic planning brings water in a cup each time, while our approach anticipates the future needs and fill up a jar during task 1 that helps reducing the overall planning cost. We also show experiments in large proctor alpha setting, details in the paper. Statistical results shows that our planner reduces the cost of task sequence by 5.38% in proctor and 31.5% in restaurant settings, and if given time to prepare in advance, using our model reduces task sequence cost by 40.6% and 42.5% respectively. Thank you.